Okay, I'm gonna try this again. So we're gonna learn how to compare two different molecules, see if they're isomers, and what kind of isomer they are, okay? So first, what's really helpful is to be able to visualize how to turn a Newman projection into a wedge dash structure. This is a Newman projection. If I draw a wedge dash structure, it is going to look with the wedges and the dashes and stuff, but I'm going to teach it, so just wait. We got A, B, C, X, Y, Z right here. And I'm going to turn this into a wedge dash structure. How the hell do I do that? Just wait. This is my front carbon, right? I can't see the back carbon, but I know that it's there. Same thing about when I look down this pen, I can't see the bottom, but I know it's there. You can see that I tried to make this video earlier and I messed up because I did the same analogy. So same thing with this. We've got our staggered structure, A, B, C, X, Y, Z. And I'm going to turn this into a wedge dash structure. And to do that, the front carbon needs to stay in the front, so it's going to be on the left. This is going to have ABC. This one's going to have XYZ. So I'm going to turn this like this into a wedge dash structure. Watch my A. It stays planar. You can see that it doesn't have any 3D qualities. It's literally just hanging out up there. Watch my B and Z. My B turns away from me. My B is back here. My C is up here. So that means my C is a wedge, my B is a dash. Same thing for XYZ, same exact process. Watch my Z, so sorry, my big ass hand. Z is gonna stay planar, like this. Watch the X and Y. This is my Y, it comes forward. So that means that my X has to go back. You can check your work. You can be like, okay, this is staggered because there's the wedge and dash on one side facing down, and this is my wedge and dash on the other side facing up. If they're both facing down, they would be eclipsed. They're both facing up, they would be eclipsed. But since they're on either sides of this bond, that means that it's staggered. So just go away, check your work. And now we're actually do a problem. Okay. So we're trying to see and compare these, manipulate one or the other, and we're going to see if they're actually, what kind of isomer they are. So I'm going to pick this one because I said so. And the best way to start these problems is to see, okay, which substituent do I want to pick on when we play freeze tag, and target that one in order to compare it to the other one. Because when you play tag, you don't go after every kid, you go after the cute girl. And this cute girl in this problem is my bromine. So when I start this problem, I want to think about what it looks like. I've got my front carbon here, my back carbon here, my front carbon here, and my back carbon here. I know that the bromines aren't on the same carbon because this bromine's on the back carbon, this bromine's on the front carbon. What do I do? In this case, the good way to solve it is to do a pancake flip. Pancake flip is exactly what it sounds. When you're cooking, you have a pancake. This is my pancake on a spatula, and I flip over my pancake. And that's what we're going to do with this molecule. And a reminder, we're doing this because the bromine's on the back carbon, and this bromine's on the front carbon. So I've got my molecule looking like this. HHCH3, H, bromine, CH3. And I'm going to do a pancake flip. So right now, it looks like this from the side. Front carbon, back carbon. And I'm going to turn it over like this. Over. Watch where my molecules go. Here's my HCH3. Here's my HCH3 bromine. Watch where the bromine goes. My bromine is a dash in the back right now. Now it is a wedge on the front carbon. So when I redraw this molecule, I'm going to write PC for pancake. And now I have my planar and then my 1, 2. So when I hold it up as a Newman projection, it's going to be one on the top, 2 on the bottom. And I'm just turning it again so I see it as a Newman projection. A reminder that my bromine was green on the right. So I'm going to restart from where I was as my HCH3, my HCH3 and bromine. HCH3. So when I turn it, my bromine's in the front again, my CH3 is in the back. So when I hold it up like this is my CH3, my H is last. Same thing when I do the back carbon. My now back carbon. Sorry, that's ugly. Okay, starting over again, my HCH3. When I turn it, HH, they're going to stay HH because they're still H's. And my CH3 is still going to be at the bottom because it's still at the bottom. That's an easy part about this problem, is that these are going to stay H's, and this is a CH3, but you do have to recognize for the future that these H's flip spots, because this one was wedge, now it's a dash, vice versa. So I've done a pancake flip, and now we're going to reevaluate. We're like, okay, bromine's on the front carbon, but they're not in the same spot because this one's facing like upside down triangle, and this one's a right side up triangle. What the hell? Well, now we can either turn or rotate the molecule, because we're not going to do a pancake flip again. That would just make it go back to where we started. So up our sleeve, we got a turn or a rotation. What if we did a turn? How do you know when to do a turn and when to do a rotation? A rotation is only doing one side of the molecule like this. A turn, if I look at it staggered, a turn does this, where it turns the entire molecule. And it looks scary, but just wait. We're only looking at our bromine. So let's go ahead and turn the molecule, because as of right now, I also see that my back carbon is not lining up with this back carbon. So that's why I chose to turn the molecule. And we can always turn it back, we can always turn it again, we can rotate it later. But right now I'm going to turn it. So when I'm looking at it up and down, here's my H, here's my bromine, here's my CH3 on my front carbon, here's my H, and my CH3 on the back carbon. So when I turn it, I want my bromine to be on the bottom. And this is kind of supposed to look like a peace sign. So these are all supposed to be symmetrical, and so are these. So don't let this looking longer freak you out, because I'm going to make this bromine go right here. I'm just going to redraw it like that. My bromine's going to go right here. Okay? So I'm going to redraw this where my bromine turned to be down here. So if my bromine went here, that means that my CH3 went here, and my H is left to place. It's on the right. So that means that when I do this part, starting over again, here's my H and my bromine. Gonna fall, just kidding, my CH3. Gonna fall at CH3 because the H's are the same. So my CH3, when I turn it to make the bromine down, my CH3 is gonna be on the left. And then I have my two H's. So we're like, okay, the front carbon's good. Yay. But what about our back carbon? Our CH3 is on the wrong side. In this case, we would not turn the molecule, because no matter how much we turn it, the CH3 won't magically end up on this side with everything else the same way that it is now. with the front carbon looking cute. So now we're going to pick on the CH3 and the back carbon. We're like, okay, why are you like this? What are we going to do? We're going to rotate the back carbon because our front carbon's cute, right? Here's our CH3, our H, our bromine. They're exactly the right place. And now we have our H, and our CH3. We want it to look like this. So that means that we can take our back carbon. Watch what I'm doing. I'm so sorry. My big hand. And I want my CH3 to be on this side. So that's what it means when I'm rotating the back carbon. And I know that it's hard to see with my hands in the way, but if my CH3 was right here, and I need to rotate the back carbon, I could rotate it this way, go all the way around like this, or I could recognize that it's already down here and turn it like this. So let's see what that does. Front carbon's gonna stay the same. I'm not gonna redraw the letters because we're focused on the back carbon. If I put my CH3, here's my CH3. If I put it on this side and I turn it, here's my CH3. And our H's are just gonna follow suit. Is it the same? Yes. We already know that our front carbon's the same, so what does that mean? When you get to this point, you're like, okay, these are the same molecule, which means that they're isomers already. We already knew that, otherwise we wouldn't have started. But what kind of isomer are they? If you do a pancake flip and you have the same molecule, you have an identical isomer. If you do a turn and you have the same molecule, it's an identical isomer. If you do a pancake flip and a turn, it is still identical, because when I'm doing this, it's the same molecule. When I do this, it's the same molecule, it's just flipping around. But the second I do something like this, where we did with the CH3, and I turned just one of them, that automatically made them conformational isomers. So this example shows that A, make this A prime and B are the same molecule, and A prime and A are the same molecule, but they're just isomers. So that's how you do that problem. And we're gonna do one more before bedtime. Okay, and if this is all looking like freaking nonsense, feel free to comment. I will give you my phone number and we can FaceTime until you get it right, because this is really hard and I 100% feel for you if it looks hard. Sorry, can I erase all this? Okay, so now I'm gonna do a problem where we have one Newman projection and one wedge dash structure, and we're gonna figure out how to do it. Okay, so these are our two molecules, and looking at it, we're like, what? But to help, we can turn one of them. We can turn this into a Newman projection. We can turn this into a wedge dash structure. Since we've already had practice doing wedge to Newman, or Newman to wedge, let's do wedge to dash. Wedge to Newman. Wait. Okay, so I'm going to turn this into a Newman projection. I'm so sorry. Okay, so we've got staggered structure where we have two on the top, one on the bottom, one on the bottom, one on the top, two on the bottom. Here's what it looks like right now. Right? Wait. Make this a little more even. Like this. Two on the top, one on the bottom, one on the top, two on the bottom. So I'm gonna make this like this, all right? And that's where you could start, but looking ahead right now, we know that this bromine is on the front carbon, this bromine is on the back carbon. So instead of turning it like this and making this the front carbon, we could just go ahead and do it like this to make this bromine on the front carbon, which is a smarter thing to do. So we're gonna do it like that because it's less work in the future. So if I make this one my back carbon, my front carbon to match this bromine, step ahead of the game. Here's my bromine. So if I turn it like this, my bromine's gonna stay on the top. Here's my H. My H is gonna be on the left. My CH3 is left on the right. Same thing with this. When this goes back, this is my CH3 because it's out at me at my wedge. Turn it back. It's gonna be on the left. And we got 2 more H's. Okay? So as of right now, what do we have? We know that our bromine is still not in the right place. And we also know that our back carbon is in the right place because it's just not. So we could do a turn, we could do a rotation. And what makes the most sense? Well, we have to change the front carbon and the back carbon because they're not in the right place. So we're gonna turn it. T for turn. Okay, so my bromine's at the top, HCH3, CH3, HH. And I'm going to turn it so that my bromine up top is at the bottom. Watch. You can see that? Yep. Bromine's at the top. I'm going to turn it so that's at the bottom. Like that. So what does that do? Go ahead and draw my little, oops, just kidding. Like this. We want our bromine at the bottom. That's our goal. So what happens to the other molecules? Watch the H. When the bromine goes on the bottom, it's going to be over here. How about our CH3? Maybe on the left. Just double check your work to be sure. What about the rest of them? So this is where we started. Watch our CH3 because the H's are going to stay the same. So here's our CH3 and our bromine's going to go at the bottom. So that means that our CH3 is going to be in this bottom right corner over here. And then we have our 2 H's left. Are they the same? CH3, HBr, HHCH3, CH3, HBr, HHCH3. Wow, wonderful. We only did a turn. Sometimes they be like that. Sometimes they don't. But since we just did a turn, that means that these 2 molecules are identical isomers. And that's it. This video is long, and I apologize. And I know that I haven't done every single kind of isomer problem, but I hope that this gets you started. And if you have any other questions about a specific problem or about anything really, I'm here to help. And I'd be happy to give you my phone number or FaceTime to make sure that you get it right. So just feel free to comment if you have any questions.